Welcome to the Biochemistry Clinic. Today we are looking at glycolysis, which is simply the breakdown of glucose to give us pyruvate, NADH, and ATP. And most of the times people ask, what exactly am I supposed to know about glycolysis? Do I really have to know all the steps, all the enzymes, all the structures, and things like that? Well, this video will help you focus on the most important aspects of this beautiful pathway. Now, glycolysis takes place in the cytosol. And we know that usually when you're in a well-fed state, for instance, after a meal rich in carbohydrates, you expect glucose to be one of the end products of carbohydrate digestion. And so the body needs energy from the glucose. So it needs to go through all the steps to produce pyruvate, ATP, and NADH. So let us look at the steps, the most critical steps of glycolysis. Of course, glycolysis has 10 steps, but we're not going to look at all the 10 steps. Now, the first step involves the phosphorylation of glucose to glucose 6-phosphate by the enzyme hexokinase or glucokinase. Now, these enzymes can be used interchangeably, but we have to know one thing. Glucokinase usually is used when it's more like an emergency. It has a very low affinity for glucose. So it only comes into play when you really have a high concentration of glucose. On the other hand, hexokinase has a high affinity for glucose. So this is the main guy, the main guy. But when you have too much glucose concentration, you see glucokinase also coming into play, though it's mainly found in the liver cells and the pancreatic beta cells. Yeah. So that's basically the difference between the two enzymes. Now, what is the importance of this step, the phosphorylation of glucose to glucose 6-phosphate? Well, phosphorylation of glucose traps the molecule of glucose within the cell. What exactly do we mean? You know that glucose is brought into the cell using transporters, which might as well move it out of the cell. So to prevent the movement of glucose out of the cell, what do? We use tactics and trap it using a phosphate group. And so it stays in the cell. In step 2, we simply see an isomerization reaction taking place from glucose 6-phosphate to fructose 6-phosphate. And the enzyme is an isomerase there. Now, step 3 is actually the rate limiting step, and it's a very crucial step, characterized by phosphofructokinase 1 or PFK1. So this becomes our control center. And of course, we know that PFK actually adds a second phosphate group to make fructose 1,6-bisphosphate. So the addition of a second phosphate group actually commits this molecule to glycolysis. And that's why we refer to this step as the committed step as well, because it actually commits this molecule to nothing but glycolysis at this point. Now, there's something very interesting that you need to bear in mind here. When there's need for fast production of ATP in glycolysis, there is this side reaction where PFK2 is able to convert fructose 6-phosphate to fructose 2,6-bisphosphate. Now, what is the importance of fructose 2,6-bisphosphate? Well, apparently, this molecule activates PFK1. So meaning that the rate or the activity of PFK1 will be enhanced by the presence of fructose 2,6-bisphosphate. So very interesting aspect here. So when you need a lot of ATP, this reaction usually takes place, so that you produce this that will in turn activate PFK1. Now, we'll talk about inhibition and activation later on. So for now, after forming fructose 1,6-bisphosphate, you notice that there's several steps here from step 4, 5, 6, 7, 8, 9, and then the final step where phosphoenolpyruvate is actually converted to pyruvate by pyruvate kinase. Now, steps 1, 3, and 10 are very critical control points because these steps are irreversible. And I want you to remember this. They will be very, very important. Steps 1, 3, and 10, very important. Never forget. Especially step 3, which is characterized by PFK1. You cannot forget this because this is the rate limiting step. And in medicine, it is our target, our control point. Now, there's something that I need to say about inhibition or regulation of glycolysis. Why do we need to talk about regulation of glycolysis? We know that this is the most important aspect of metabolic biochemistry, the application of a pathway. How are we going to control this? How do we make sure the body has enough pyruvate or ATP? Or how do we inhibit? So you notice that there are things like ATP and citrate which inhibit PFK1. So meaning high levels of ATP and high levels of citrate will definitely inhibit PFK1. So meaning that glycolysis may not proceed in the presence of high concentrations of ATP and citrate. And I think this makes sense because ATP is one of the products. So if you already have enough ATP, why should glycolysis continue? So this makes sense as an inhibitor. And about citrate, we know that pyruvate can be decarboxylated to acetyl-CoA, which goes into the TCA cycle to produce citrate in the first step. So we know that when we have an abundance of citrate, there's absolutely no need of us to continue with glycolysis because PFK will actually be inhibited. Now, AMP activates PFK1. So we know that AMP signifies that probably we do not have enough ATP. So if you have high levels of AMP, you are likely to activate PFK1 so that you produce ATP. So this equally makes sense. And also, fructose 2,6-bisphosphate activates PFK1, like we just said. Now, the conversion of fructose 6-phosphate to fructose 2,6-bisphosphate is catalyzed by PFK2, which also has its own regulation. For instance, glucagon may inhibit this enzyme, so you may not have this produced in the presence of glucagon. But insulin, on the other hand, will activate PFK2. So when you have high levels of insulin, this reaction is a very serious possibility to produce this, which in turn will activate PFK1. So the other thing that I would want to mention before I conclude is the medical application. So we have so many medical applications of glycolysis, but this is actually what matters most also. How do you apply glycolysis in the field of medicine? So for instance, the aspect of inhibition. If you inhibit PFK1 in your red blood cells, you expect glycolysis to be shut down or to be halted. And once that happens, you expect that the red blood cells will be deprived of ATP because we know that the red blood cells do not have mitochondria. So more ATP is produced in the mitochondria in the other cells, but your red blood cells do not have the mitochondria. Therefore, they depend on ATP from glycolysis. So if you shut down glycolysis in red blood cells, this could lead to destruction of red blood cells, which may lead to hemolytic anemia. So basically, that is what you are supposed to know about glycolysis. Do not miss the next lecture. Thank you very much.